Okay, hello everyone. Welcome to a working session of our, physics project, except that we are taking the formalism of the physics project and applying it to other areas. And right now we're talking about metamathematics. And we have been looking at a bunch of things to do with theorem proving. And I have a question actually, which is, what's a good example of a confluent rewriting rule that we can use here? I mean, we presumably can use, if we just use the AB equals BA, if we have string rewriting,
yeah, sure,
and we have something like, let's just do over here, we say confluent rewriting. Well, actually, we know if we have the string rewriting case would be something where we would actually have this. I mean, what we need is associativity. Is that right? To have something that emulates string rewriting. Am I right? Is Nick with us? Is it that?
Yeah.
yes.
Well, if you want, you can use that find string proof from the source function, right? From the repository. That just does exactly that, adds an associativity to a string operation.
Okay, so let's take, for example, our AB goes to BA. No, BA goes to AB. That's not, sorry, I should have done. And then I want to say, I see BBB AAA goes to AAA BBB. Why did that not work?
Oh, just
because I got the argument. No? Find string proof. What am I doing?
well, you have theorem and axioms.
Yeah,
so axioms are your rules.
I'm totally confused here. Do I use equal signs or do I use double arrows?
I think double arrows.
Yeah, because I think
Two
equal
rules.
sign, like this. Oh, lovely. Okay.
Yeah.
But now, is this going to give us, if we did this, would it work here?
It should.
Okay.
You may replace like this first argument because it got like string logic, rename it to equational logic so that these boxes would work. I don't know, at some point they stop working.
Okay. All right. So then we just say, why don't we just do a hackalola here and just say string logic, arrow equational logic. Oh, wow. Oh, look at that use of by substitution up there.
Yeah, nice.
So, okay, string wise, let's just see what this is doing. So let's make a display here. How would we do that? Where we want to take these things and we want to take the circle dots and just replace them with them. Well, actually, do we need to do that? I mean, is this
String join?
No, it's not going to work because look, it matters which way the parentheses are going. The reason this is going to, all the effort it's going to, is rearranging parentheses, I think.
Yeah.
But at least let's get rid of the actual characters, the slash dot characters here, and maybe we can do that by just saying, how do we want to replace them with pure spaces? How do we do that? We basically want to take, I mean, these are not vertex. These are vertex shape functions of some kind, yes?
I think it's vertex shape function just as the box. So it's still a vertex with those operators and equalities and symbols.
Okay, but so what should we do to get rid of that? To rewrite the vertex? Oh, you mean
vertex supplies should work.
Okay, all right.
And you can do it.
Okay, fine. So let's just get So with G equals this graph, and then we say vertex list, well, vertex replace of G, and then we've got the vertex list of G, and then for that we want to say, what should we do? You just replace it with a row. Probably
No,
reasonable.
just make up a rule like V blank goes to like replace all this, what is it, center dot? Or
I want to get rid of it altogether. I want to have nothing visible there. I want to just say, you're suggesting I just do graph G.
no, my suggestion was to go just vertex replace.
Yeah, we got to do
G
vertex replace.
and make a rule delete with there.
Yeah,
without
yeah.
any vertex list.
How does that work?
Yeah.
Okay, like this. And then we say, we want to take circle dot, v slash dot, circle dot, of A blank, B blank goes to row AB. What happened here? Let's close the vertex replace. Wait a minute, what is going on here? Close for the, that's closing for the row. Oh, I got another one of those. I don't understand. Oh, look, it's got one of those done, but not all of them. Is that right, or does it, is it, no, I guess that's right, because it removed the parens, but I guess it was okay to do that.
Yeah.
Oh, that's really
Should be
boring.
okay.
Oh yeah, I see. That proved the tautology.
Yes, yes.
The BBBA
Mhm.
goes to whatever. And okay, so this is an example of a confluent rewrite rule. How can we see that from this picture? Is it the fact that there's a single chain here that reveals that, or what? I mean, let's try another. Go ahead.
You shouldn't. Well, we can see it from this picture because it's only one
Right.
particular path, right?
I
That's
see.
not the point.
We've seen plenty of examples that have this exact same structure, and I doubt that those are all confluent, right?
Right. I see. I see. Okay. Well, should we make one attempt at doing this search and just see whether it goes blindingly fast? And if it doesn't,
Sure.
yeah, maybe.
Small one.
I mean, I'm wondering whether I should run this on let's run it maybe we should do a remote batch submit and try and run these somewhere else. If we're confident it's going to run, then
Are we?
no, we're not. I want to see the first one run.
Good. Yes. Okay.
This one here, I mean, this should run very quickly. This should run in a few minutes.
Okay.
So let's try running it again.
Yeah.
Okay, machines launching. And the machines look like they're launching a lot zippier, more zippily, which suggests that they had zombie processes running on them before.
Let's hope. Let's hope. Good.
Why is this taking significant time? Is this doing something different from what it did before? Because before, I mean, at that speed, it's going to take a while to run through all of these. What were we doing here that's different from what we did before? So triax 3. Takes an axiom and it runs it for all statements of this kind. It runs with that axiom. Wait a minute, what are we doing down here? Oh, I see. Here, we're running across all axioms of this type, which we didn't do before. Right, that's the new thing. We're running across multiple axioms. Previously, we just did a single axiom there. Well, arguably, see, some are running much faster than others. Notice that that one that ran, and we should record how long it takes to run these. We could put an echo timing around them.
Timing, yeah, right.
Because it may be that ones that are generating lots of critical pair lemmas take longer to run. All right, this is going to take a little while. So let me try. Let's try running this as a remote batch job. Okay, and then we can go back to our work and see what it does. Okay.
Mm-hmm.
So I guess I'm going to kill this. I mean, we'd wonder slightly whether this. So I mean, our criterion is we get 2 by substitution steps. Could Roger please look at the thing I just asked him to look at? Okay, let's see if we can. Well, let's see if we can kill these. I don't know whether it'll even work to kill these, and then we have to see whether these processes stop running.
Right. Mm-hmm. Okay.
Okay, let's just try aborting. It aborted, how amazing. Let's just see if I just say parallel evaluate, tell a machine name, and then I do counts. Okay, that's nice, came back quickly. Okay, good. All right, let's do remote batch submit here. Okay, so I have to remember, where do I have the information? who has the information on how I do the remote batch submit? We should have this information, and Roger, we should include this in the parallel tools collection. But do we know where it is right now? Roger, could you get off mute? And
Yeah, no, I don't.
You
You
have no idea?
have, well, you've got the credentials stored.
but where is a
Right.
sample of how to use remote batch submit with the correct with the correct
it's in your local functions. It's
okay.
at physics co-development
Okay.
SW local functions, AWS.
Okay. Thank you. We're hearing a lot of clicking. Sorry. Still, somebody could probably move their microphone further from their keyboard or mouse or something. Okay. AWS. Okay, so this, by the way, Roger, is also this is from January 2021. Okay. Well, so let's do here. Let's get rid of these because we don't need these for sure. We don't need that. Okay, so now we're going to say here, additional cases. And up here, we're going to say remote batch job. Okay, so let's get our environment variable. And Roger, this should be the stuff that's in the instructions.
Sure.
That does not seem good. System internal failure appears in multiple contexts. Oh gosh, it's in general utilities. You know, Nick, we should not be using general utilities. Just as a formula for horrible things going wrong.
Okay.
Really,
You know
really,
that-
really shouldn't. I mean, I don't know what you're using from it, but we you know.
Yeah, why do you often include it, Nick?
No, just a few functions. I don't use anything serious.
Okay, well then maybe we should get the few functions actually put in the function repository, and then you can use them from there. All right, let's see if this works. Okay, so this is, we're claiming we're going to run this here remotely. Let's see if we can do this. This is right, as far as we know. Let's see what happens. Okay, one job submitted. Okay, let's see. One thing I should have put into this job is an email that tells me it's done. It doesn't do that, does it? It doesn't automatically email me. Is there an option for getting it to email me? Okay. Okay. Just okay. All right. Let's turn to a different topic. Okay, this is now happily chugging along. So the topic we're going to turn to is empirical mathematics and its use here. We will be returning later in the day to automated theorem proving. Okay, so this I was looking at. Okay, these are axioms of Boolean algebra, and here we've got named theorems, which I got out of the notable theorems collection.
Right.
I think it's a bit bigger. How many will it get to? What project, I wonder, will be the one that gets the largest number for its unseparated?
Well, how many were there when you wrote the physics project book?
a lot more, but the point was there was a single directory for Physics Project, and arguably what we should be doing is making a subdirectory for these projects. That's probably what we should be doing, rather than
Yes.
having immunology 1, 2, 3, 4, 5. Okay, so here we got a lot of background noise. Here we've got we have to remind ourselves what was going on here. Pure equivalence graph. Okay, the entailment cone for original axioms. Where do the named theorems show up in the entailment cone for the original axioms, for the axioms of Boolean algebra? So what is this multi-way rules nest graph? Is that the right thing here?
Yeah, I think so. It only performs substitution.
Okay, do we have a bisubstitution analog of that, or is that not possible?
It's possible. I think we have it. Let me check it.
Is it equivalent to remove events of the okay, by the way, I'm concerned that in other places, well, this is a bit confusing because this will have a single, I mean, usually in a cumulative evolution, there are multiple theorems that, it's two theorems gives you one new one, right? Whereas in this multi-way nest graph, there's one theorem giving you a new one, correct? Which is not really what we want. So I think what we want here, let's first of all generate the token event graph version of this. So how do we do that? We want to say, you've got a nice function, and I now forget what it is. Token, what is it called?
Token event substitution graph or what?
Yes, that sounds exactly right. Okay, so let's take a look at this. Let's take a look at one step, token event substitution graph. But what's this doing? That we shouldn't have that there. This is now a pure token event story. Okay, so that's now the entailment cone from the axioms of Boolean algebra. Do we have a nice way, and maybe we need an option for this, to let's do the cleanup for the blanks and so on. How would we do that?
Use vertex replace.
Okay. Okay.
Symbolify. Maybe just symbolify.
All right, and I think we might as well also, yeah, all right, let's just do that. Okay. So that's after one step. Boy, what a complicated mess. Wait a minute, where are the, oh, I see, there are some events there. Wow, this is a complicated mess already. So a question would be, what's that?
Yeah,
So
because there
after
are a lot of axioms.
I know, right.
And we
So-
usually don't use that many axioms. That's why
I know.
Boolean's explosive.
So let's take a look here at the famous axioms, notable theorems, and let's okay, so what we either have to do equals equals here, or we have to do, should we do that? Let's do that. Let's make it more mathy. Let's do this, and let's say slash dot. Hopefully that won't slash dot two-way rule arrow equal.
Actually, Nick, didn't we discover that it's really just two variable generating axioms that are responsible for most of this, most of the explosion, right?
Look at that. That's annoying.
Oh yeah, right.
Do we have any way to deal with that? Well, actually, maybe that isn't so bad. If there's only one of those,
I only see one.
what that's saying is that everybody eventually should lead to true.
Yeah, well, there's gonna be always be a one if you do it, because they're all gonna collapse as soon as any of them go like evaluate to true. Then it's gonna be just one vertex remain.
I see your point. Okay, so we may or may not want to have that, but let's to begin with, let's okay, so now what we want to do, so this is showing from the initial axioms. Let's for fun, I just want to see what happens in my axiom system. Okay. I think we had, this is what we wanted to cover elsewhere. Okay, so there's, so that's just telling us that some of these things give true. Yeah, this is already kind of complicated. And I'm sure if we have by substitution, it's going to be much worse. Let's take a look. My gosh. So one thing that might be worth looking at, forget the two-way rule goes to equal. Let's just ask the question. Okay, so these will be the theorems. What a complicated mess. "28 theorems approved at the first level in the entailment code."
You have an E variable too. Wow.
Oh, wait a minute. I got that wrong here. Well, yeah, we have an E variable. Why not? I mean, it's going to generate variables.
No, I know, but even in one step.
I'm not surprised. I mean, that is the nature of an axiom like this. Okay, but we can ask the question, and in fact, this relates to another section much higher up. This really wasn't supposed to be the subject of this section. I mean, this section, we really want to identify where do we get the well-known axioms. But let's just, for the hell of it, let's just see here. Oh my, this is. Well, it's big. Metamathematical space is very big. I noticed questions on our live stream about active inference, and Carl Friston, I don't know anything about his work. Maybe sometime I could talk to him. Those discussions always take effort, but maybe sometime I should. Well, this is not encouraging. Wow, we can't even get to 2 steps. That's quite something. Is there any way we can?
We can add some tests.
Prune it. Yeah.
Yeah.
Well, we can add a test that prevents. Okay, the thing I really wanted to do back up here was to find where the notable theorems do or do not occur in this list. Okay, so I think these are in the same format except for the equal signs. Oh, they're even in the same format with the equal sign. So we were looking at how would we want to do this? Well, let's just say vertex list %93 equals sign there. Okay, so that's going to be all of these. And now we want to say map over notable theorems. We want to say position in this of, well, let's just do the following. Let's say, yeah, of first of hash, and then let's say hash arrow, position first of hash, map over notable theorems. Oh no. Well, commutativity for and, commutativity for or are axioms, which is rather unexciting there. Okay, well, let's see. Do you think we're going to be able to go to the second level here? Well, let's see with by substitution whether we can get anything here.
What, for one iteration?
Yeah.
Yeah.
So we can get by substitution here. I don't know how absurdly large this is, so let's just find out. Oh, we got it. Okay, so vertex count, that, 280. It's not huge. Well, okay, so at least if we do the, all right, well, let's try. There are the vertices, and now we want to say that is very disappointing. Did we do something stupid here? Is there any?
Well, there is some. It found some, right?
No, but those were in the axioms.
Oh yeah.
It's just one iteration. I didn't really expect it to find anything. Did you?
Well, let's give it a bit of a better opportunity here. Let's say for these, let me just do the following. Let's just say reverse /at, just in case there was one that was the wrong way around. Pathetic. Oh, what about variable renaming? What about variable renaming? Because that can happen, right? And what we really want to do is find out if there's a match up to variable renaming.
You shouldn't even do a simplified patterns.
But
Just
then what do I do?
Match Q of your notable theorem against it.
Yeah, that's a good idea. Okay, that's a very good idea. All right. Okay, so then let's just do here. That's all I want. And now what I want to do, actually what I want to do there is vertex list of that underscore two-way rule. Okay, now in this case, what I'm doing is I'm saying for each of the notable theorems, I want to know, yeah, this would just, is this the right way around? Yes, for each of the notable, no, it's the wrong way around. It's the wrong way around. I want to know, does the notable theorem do any of those patterns, right? Do any of the patterns that are in there in VVVV? So let's pick a notable theorem. Let's say this one here. Oh, actually, one thing I could do. Am I being stupid here? No, we have to go through each pattern, right? We have to go through. So if I say take VVVV, comma 6 or something, I'll see a bunch of patterns there. Okay. Now those have two-way rules in them. So this we have to replace with a two-way rule. And then we can ask the question, does this rule here, the law of absorption, does that occur with a two-way rule? And we say position, no. We would say we map over VVVV.
You can do position.
How?
You can use position. You just make a reverse co-match, So you take a position of your vertex list and then ask for, make a conditional.
You mean in alternatives?
No alternatives. You still have a one to look for position in your vertex list, right? So the first argument is always going to be your vertex list.
Yeah, but fine. But I mean, I just want to do the matching. Let's do the following. We could just take this and we could say match Q. I always forget the order of arguments for match Q.
Pattern is the last one.
Pattern matches this. Okay, so then we say this hash sign / at, and then we say VVVV, and then we would say position in that of true. Splat. Okay, so now we want to say for each of the patterns, we want to say function. And here we want to say replace equal with two-way rule. And now that is a function of this notable thing here. And we want to take that and map it over the notable theorems. Oh, except. We want to say match Q first of not.
That's
all right.
Yeah.
Oh, that is depressing. Look at that. How can you not even get the idempotent law?
For just one step.
It's just one. I don't find it that depressing. If you could get most of the axioms in one step, that would be somewhat depressing, right?
No, most of the notable theorems in one step.
Yeah.
Okay, so maybe we should run this and find out how long it takes and find equational proof to get each of these. Okay, so let's do that. So then, well, all we have to do is say find equational proof of hash, comma, Boolean axioms. And then we say, where's your lovely thing for doing, what's it called? Proof object to token event graph. Say that again? Okay.
Proof object to token event graph. Correct.
But we also have the thing for, well, here, let me just, oh, we just did this here. Find replace paths. What is this doing? Is that using find equational proof? Find replace path?
Yes. Yeah. Cut elimination. Yeah.
Okay. Okay, so there are the accumulative proofs. That's the thing we were looking for here. Okay, so this one, what's that?
More than one step.
I can see that, though these ones are only 2 or 3.
Yeah, we can try to find those. On the second iteration, maybe. Not guaranteed though, because it has
Well,
3.
Yeah, I know it's got 3 here. Let's just. I just want to. We have this nice way of displaying these, which uses. I mean, we should standardize this display. This isn't quite right though. But there, we also don't want orientation to left. And we want aspect ratio is like 1. And then we want to say, find equational proof of this, comma, Boolean axioms, hash, comma, Boolean axioms. And then we want to say labeled of that. Wow. Oh, no, that's the right thing I've got. What happened to that? What are those green things? Oh, you made them green somehow.
I think the green in the original proof graph. Those are axioms.
Yeah, right. Okay, well, this is a nice picture. I mean, insofar as it's right. So this indicates how difficult it is. So those are De Morgan's laws, and those are quite difficult to derive. I'm surprised these are so difficult to derive. Okay, well, I admit these don't seem like they're very entailment coney.
We won't reach them. No way. No way.
We can try them, find them with pruning.
With which?
If we add pruning, we can try more than one step, 2 or 3.
Right. Well, let's see how big these got. I mean, let's just see, in this case, how big did it get? Let's look at the distribution of sizes of expressions in find equational proof. Okay, so let's say find equational proof, and then we would say of the expression, comma, Boolean axioms, and then we want to say, and now we have proof data set, right? And I think we were doing this before. We want to say, let's just get one of them here. Let's get one non-trivial one. Let's do guy. My gosh, what is it taking all this time for? What is it doing?
Oh, it's a long proof.
It's not that long. Wait a minute. Oh, big problem. Yeah, the problem is that this Boolean axioms, that the thing here needs to be replaced with v goes to whatever it is. You know what I'm saying?
Oh, so circle plus. Circle times.
Yeah.
Right.
Circle plus.
Okay, more like it. Okay, so now we want the proof data set here. Okay, so now we want to take that, sub all, comma statement. And what do we get for that? And then we want to take values for that. And then we want to take normal of that. And then we could just count the leaf, do the leaf count here. What do you think? Should we use leaf count? We could certainly do leaf count here.
Oh, you can also run this function that I have for fixing the conclusion. You can run it on the data set, like fix data set or something. Fix.
Okay. We can do that, but that's probably a less important thing. Okay, so these are comparatively, okay, so these are leaf count 9. So let's just run this across the whole thing. Just to see what those are like. So let's say this is first of hash. Let's say histogram, these labeled hash / at notable theorems. What did I do wrong? Oops.
You forgot 10%.
That's a problem. And I should have done this in parallel. Oh, there we go. Well, that's kind of interesting. So that tells us that in the intermediate stages, we never go beyond about size 15 for these rules. So let's see in the entailment cone, if we make that restriction, what happens? Okay, so let's go back up here. And then we want to do a leaf count restriction on this here. Circle times goes to wedge. Actually, we want to do the whole thing there, probably. Let's see, which way around do we want to do this? We want to, no, we don't want to symbolify. We simply want to look for this. We want to do the exact same thing that we did before, but we want to, so where did we do that? We did the search here. Yes, so we want this thing here and this search here. So this will be the case where we restrict size of intermediate theorems. Okay, so how do I do that? I put that into token event substitution graph. After this one, what do I do here?
It's pattern test option. I think you're adding more selection, but I think that's going to be all right. So that's going to be a function, right?
Okay.
It just says which tokens to consider.
let's just do this for the time being. Let's give it let's give it a little bit of leeway. Okay. All right, so let's say length of EVV, only 8. Really? Oh, this isn't going to work because we have to do the symbolify step. Otherwise, we will. Yeah, we have to do this because otherwise it's going to otherwise it's going to count the pattern variables in this.
You can do it inside the test.
I know we. Oh yeah, that's an interesting idea. Okay, so we just say symbolify patterns inside that test.
Right.
Okay. So now there's VVVV, and there's nothing cooking there. Okay, so now let's do this again. For 2 steps of substitution. Now, hopefully it won't get, actually, we're going to want to know how big it is. Oh, you can't be serious. That even this doesn't work. Wow.
Well, just to estimate, out of those 125, how many have leaf count less than 60? That's
well,
how many. No, pattern test is for considering which tokens to combine, but the result is not discarded.
Oh.
So I think, yeah, so this pattern test will only take effect on the second step. So out of those 125, it will only consider tokens that has leaf count less than 60.
Okay, well, let's be more draconian here. Say 8. I predict this is close to 0. Oh, wow. Okay, well, let's see what that actually is. Okay, I'm going to keep going with this and see what happens after 3 steps. Maybe it'll only give the same theorems again. I think it's going to give the same theorems again. Yep. Okay, so there'll be some value at which it starts escaping. But I think at that value, it's already going to have trouble. Let's go to 11. Okay, this is kind of interesting. Bluff. Okay. So we could try doing this. Okay, so basically, it's pretty hard to find. Surprised we can't find any of them. Like A equals A. This one here, I'm just really surprised we can't find that one. But I guess that.
Well, it should be 3 steps. If you find the equation proof, actually found the shortest one. So we can find it. We need 3 at least.
Yeah. Well, I assume.
And by substitution steps also.
Right. Well, let's try by substitution with size 8. Oh boy, this probably was a mistake. Oh, it came back. Okay, let's see what this does. Bluff. Okay, so 8 wasn't enough.
10?
I don't think it's going to come back with 10. I mean, I
Well,
think
you weren't sure it would come back with 8. Maybe 9?
Let's try 9.
Come on.
Can we do any of this in parallel?
No.
It's a question on our live stream. Is this being derived from mathematics being true, false? No, this is a constructive setup where you start from the axioms and you try and determine what is symbolically deducible from those axioms. You don't have to have a notion of true and false yet. That's a later derived notion. This is merely the structural question. All right, we're going to turn to a different topic in a minute because this is definitely not going so well.
Wow.
Actually, now I'm now curious whether
Nick, do you think we can find this first theorem here, the one that Stephen's highlighted in draft 4?
I think we can. But notice it used 2 critical pair lemmas here.
Yes, yeah, I can see that. Yeah.
I don't know whether it needed to.
Well, Nick, it's the shortest path, right?
Oh, we don't know. Who knows?
Didn't Nick say?
We hope it is, but I mean, that's that's the magic of theorem proving.
Hey,
Oh, look at that.
come on.
Let's see.
Come on. God, this feels like almost like gambling.
Ta-da!
Oh!
We got him. We got one. Look at that. We got no, those that almost look at that. We got 2 of them.
Oh, we got LEM. Oh, this is a great fishing story. Yes. Look what we caught.
Well, that's cool. Okay. All right. So now what we got to do is we got to show in the entailment cone. This is cool. This is cool. We found something in the entailment cone. A fish was caught in the entailment cone. My question, Nick, why are you not pruning based on what am I saying? Based on final leaf count. That is because this is going to have a lot of tentacles hanging out, which we actually probably don't care about. Let's try and actually make the picture of where this showed up in the entailment cone. Okay. This is going to have 1,000 nodes, and this is rather exciting, actually.
Should have saved the graph.
What's that?
Sorry?
Should have saved the graph.
Yeah, we should have saved the graph. I know. Okay. All right, let's compute this entailment cone, and then we think about what to do with it. So this is now, let me, there's not much point in me having, let me say token labeling arrow false, right?
Definitely. Don't label 1,000 tokens.
Well, this shouldn't be that bad, actually. Let's just evaluate this, which we know is going to take a little while. And then we have to know, we know that it is node 8790, right? A numbered node. How do we get to a numbered node? Oh, I guess we can just, because oh, I see. Let's get the numbered node in VVVV, which might or might not have the same specific form as this. Right, so before VVVV disappears, let's get to the numbered node 790 in VVVV. And the numbered node
You want double bracket?
I do indeed. The fishing rod is straining as this deep sea fish. Okay, well,
Parmenides managed to find a fishing emoji for us.
Okay, come on now. Questions from Timecake about Bayesian inference and the Rulliad and observers in the Rulliad. These are interesting questions, but with very, very different topic from what we're dealing with today. Okay, what I want to, okay, we're going to have a success here. Let's just savor this for a moment, and then we need to go on and look at what I really wanted to cover here, which was up, there we go.
What's that thing? Yeah.
Okay, here we go. All right, so now, well, let's just do one very basic thing here. Let's take graph EC edge style goes to opacity 0.2.
Yes.
That's a really simple thing. And then let's start to, okay, there we go.
Yeah.
Now,
but again,
I think we should prune. I think we should prune the edges that have, oh, I want to see these here. Okay, great. Those are the actual vertices. Now, can we prune the edges that have, can we say vertex delete with a criterion?
Yeah.
Okay, so let's do vertex delete of, let's say, line 147, and then let's say leaf count of symbolify patterns is less than 9. Or I want to say, how do I do that? Do I just give a pattern?
Yeah, you have to use condition. V. Without ampersand. Just replace hash with a V.
Yeah, I was thinking question mark. What? How can that be right?
It also removed events.
I see.
And disconnected them.
That's kind of weird. So what this is saying is, I don't understand this. It's saying this is knitted together by things that are, what happens if we do that? This is very odd. So let's take this and let's say vertex list VC underscore two-way rule, and then let's say symbolify patterns slash at this, and then let's say we want to say leaf count, and then we want to say histogram.
So
Well,
it's
they're mostly of size 13.
yes.
So in other words, the thing
It's knitted
knitted
together
together
by a minority.
by some larger things.
Hmm?
Huh. Oh, don't let me forget to take a gander, a look at our other job and see how it's doing. Okay, so let's say here, graph EC. Well, actually, what we really want to do is now say highlight graph.
Oh, I had a find path function that searches a path in the given token event graph.
Okay.
Find proof. It's just called find proof.
So what should we do here? We should say find proof. No, that's not.
Lowercase find proof. List of axioms and hypotheses. Yes. Yeah.
Okay. Okay, that's good. Let's do it. List of axioms is axiomatic theory TWP of this, right?
Mm-hmm.
That's rather irrelevant to us here. And then you want hypotheses, right?
Yeah.
I knew this should have been on a list. I was debating whether to put that on a list.
I'll try one of them. I'm not sure whether they would work
Okay.
in the list.
Okay, like this.
Yeah, hopefully. Oh, you already simplified, right?
Symbolified what?
Your vertices.
In the graph.
Yeah. Because no,
Does it have equal signs in it?
maybe.
No, this doesn't symbolify. This doesn't. Does this work with patterns?
That may be a problem. I'm not sure.
Well, let's just change this. Should we just change this? We can symbolify this. Well, here. EC. Okay, so here we would say vertex replace of V underscore two-way rule, right?
Mm-hmm.
Like this. What? What does it mean missing of axioms?
Well, your axioms are patterns, so you have to simplify them too. Oh, you can find them in the graph.
Oh, I know why. Because we've got V and wedge. Ta-da!
Now you can use it as a subgraph. Well, first of it. So first.
But is this a sub? I mean, is this a okay? So so graph of first to percent. Well, that's pretty interesting. So that's what this is actually like inside the token event graph.
Yeah, I think it should be the same as your find equational proof if we compare them.
Yeah, quite possibly. I mean, let's see. Can we do this with the labeling, with the same labeling? Is there an easy way to do that?
Or just take the subgraph.
I see. Subgraph of this thing here of EC. And we could just take of this, right?
If they're the same. It's hard to keep track what is have patterns and have symbols already.
Yeah, I know. So which one was this? This is, I think we have to do this here.
Okay. Weird the graph.
And let's do vertex labeling. Okay, there's our result, right?
Mm-hmm.
And that's a little bit differently set up from the find equational proof way of doing this.
Yeah, you can see a two-way rule A is in the upper left-hand corner.
I don't know what the heck that's doing there. Well, let's see what the find equational proof version of this is.
Mhm.
You have that in the other notebook. Okay, which was this? This is A bar. It's that one there, right?
Yeah.
I have no idea what the precedence of that creature is. What do you mean it has the wrong?
No, you put the parentheses under the overbar.
Under the bar, yeah.
Oh. Oh no, I don't need parentheses if I do that. Okay. So now if I say,
Vertex shape function.
what do I want to do with it?
Just remove it. You have it go into automatic. Just remove this piece.
I might want to remove the vertex size as well. Lovely. Okay. So this okay, so that's those are the axioms that it's using. It's using 3 axioms here.
Yep.
It's interesting that this is full of by substitution. Oh, that's because we did by substitution only.
Yeah.
So this managed to do some of it with pure substitution.
Well, those by substitution may as well be substitutions. They just
Right.
I see. Okay. But it got, this one has 5 events. This one has 6 events.
maybe just it's
Go
not
ahead.
the unique one. You can try more because find path can return more than one path.
Okay, let's do it.
Try like add
Fine.
2
Proof here.
last
Okay.
argument.
Well, let's live more dangerously. Let's find 4 of them. Okay. And then for each of those, we say graph, we map graph over that. Oh, wow. That's cool. So now we'll map the subgraph here over those. That's kind of complicated.
Yeah, I think the first one's going to be always the simplest one.
All right.
Maybe not. I'm not sure.
Well, let's try. Okay, so this is how that thing is reached in the entailment cone. It's really pretty interesting.
Yeah.
I mean, we should put the axioms on the top level somehow. I don't know how to do that. Do you know how to do that?
Well, try root vertex and just list them, list the axioms.
You can include multiple roots,
I think,
so
yeah.
to speak.
Yeah.
Okay, cool.
Okay, so fine, let's do that. Root vertex arrow, and now we've got to get these axioms in some reasonable form. So where do we get the axioms? So what we have to do is, I think it's symbolify patterns of axiomatic theory, this one here. Oh, and then we probably need that. Well, let's see. Maybe it didn't like the fact that we had things in here that were
Yeah, that's not a part of this proof.
right. Okay, so let's say with that subgraph equals this. Let's get rid of this. And then what do we want to do? Intersection of this root vertex. Intersection of vertex list of SG with this.
Yeah.
Oops, vertex list of SG. And then the symbolify pattern thing. Okay, that's the root vertex there. That's the layered digraph. Close for the graph, close for the width, and make it happen. It's a little weird that that's, well, I guess that was where the line break was. It's a little odd. Huh. It's It's a bit annoying that this doesn't lay out down the page, so we're seeing, this doesn't look very entailment coney, right? Because you could pull that vertex down.
Sure.
We might want to have some other kind of layout. I'm not sure what the right way to do it is. Maybe Brad could look at this, try and figure out how to do this.
Okay.
Unless Brad already knows. Okay, that's a better case. But this is very, very cool. It's very cool that we can do this. Okay, and while we're at it, okay, so we had a second one of these. We'll have to go back and, okay, so in here, we should be able to indicate where those vertices actually are. And what you're suggesting is we can indicate where one of the subgraphs is. So let's just do that. Let's just do that. We've got this subgraph in EC. Okay, so let's take this subgraph. Hold on, so let's take this. Let's package it all up. Okay, we're taking the subgraph there. Now we're taking that as a subgraph of this. So we're inserting that stuff into there. Okay, so that will give us this thing there. Let me just copy that down just so we remember how to do this. Let's just use that there just to, because it's convenient to see that. Okay, so now that subgraph is a subgraph of EC. So we want to highlight graph. Graph EC, edge style, arrow, opacity 0.2. And now we want to say that thing there. Oops, didn't mean that there. That subgraph is the highlight. And then let's say style of that thick red.
Well, you're replacing vertices.
Oh, well, I see two little red dots. That's about it. See that?
One of them is simplified.
Maybe we need symbolified patterns in the original graph here.
Yeah.
Do you think so? So this is.
Yeah. This way it only highlights events.
There's a certain virality to the whole thing.
This is because of the two rules. No.
So what should we do?
This is the case when two rows become a problem.
Okay, so how do we deal with that? We replace the two-way rules here, right?
Maybe in the subgraph, well, both.
We got to do it for both.
Yeah. Maybe a left-right arrow, so that wouldn't evaluate.
Hack. Do we need to do it here? We need to do it here as well, don't we?
I think so. Yeah. Well, maybe you should just vertex replace this after you're getting the subgraph. Easy.
Well, I'm now almost done it, so let's try this. Okay. I mean, let's try something absurd like thickness 1.
I think something wrong.
Yeah, it's not there. Okay. Well, this is finding a subgraph there. Well, let's just echo the subgraph. Ah, well, there's a problem there. Okay, so let's do what you suggested. Let's get the subgraph first. This is the subgraph. Let's take the subgraph and let's do the same vertex replace. The subgraph has already symbolified patterns. So now we just need to do a vertex replace on the subgraph. Of this here.
Close bracket. After the left.
After which?
Right. After left right arrow. Vertex replace.
Oh, come on. Okay, let's echo this thing. I am confused. Okay.
Maybe it's not an exact subgraph because I think I add additional edges to indicate some transformations.
Oh. Well, let's do the following then. Let's at least get okay, so let's do the following. Let's just get the vertex list out of this. Right? And then we can at least get oh, come on. How do we get, maybe it's point size? Well, that's a good sign. There is at least one point there. Okay, we gotta clean this up. But we basically the basic point is we can fish theorems out of the entailment cone.
Yes, that's the point.
Maybe just make an edge list. Try to highlight the edge list.
Okay, all right, okay. Instead of vertex list. Well, let's leave that vertex list there. Let's do another one for edge list. That's not so hot.
Yeah, that's weird.
So something went wrong there. Okay. Well, I think this is great, and we need to go back and understand how this fits into other things we have. But okay, so let's just summarize what we managed to do here. We managed to take the standard axioms of Boolean algebra, and we managed to find in their entailment cone interesting theorems. Now, in general, right, okay, so the thing we were really trying to do, he says, is let me just look at that remote job for a second, see whether it did nothing. The job succeeded.
All right.
Okay, now let's just say job. I have to remember how to do this. What do you know? It worked. Although, well, it worked just fine. Brilliant. All right, emboldened by that, we're going to do another one. But look at this one. Most of these, there were just no true theorems.
Yeah.
And it may be obvious that there are no true theorems. It may be that there are variables there that just can't be matched. That basically we have what amounts to our famous Rullial virus. Go ahead.
Well, zero, I think it wasn't zero meant zero critical parameters. So.
Oh, you're right. So there were many theorems. Sorry, I'm misinterpreting this. There were many theorems, but they didn't. In fact, this may be exactly a principle of explosion thing, where basically every theorem was true.
Well, the point is that very few of them proved theorems using critical parallelism. That's the point.
Yes,
right?
although sometimes there are critical parallelisms used, like this case here.
Yeah, right. But it looks like is it the minority of the case? Minority of the cases. I can't tell.
Yeah, okay. We are going to run another one here. This is so exciting. Let's go ahead and run the next case up. Another submitted job. And why don't we actually try?
Didn't you want to get an email notification for that?
It would be nice, yeah. Okay, hold on a second. Well, I'll do another one and send myself an email for that one. But now let's see, we want to define triax for, this is very nice technology, the technology for submitting these remote jobs, really nice. Okay, but I need to be careful because I want to say echo function of the whole thing. Remember how sendmail does this. I think it's subject line. Subject, comma, body. Okay, and the body could be, it's going to get very long here. Let's just say, let me not gum up my email with a multi-megabyte thingy. Let's just say length of hash. Okay, do you believe in that? Nick, any comments on this?
I have very small experience with SendMail. Not sure. Have to just hope it works.
Well, but that's right. The echo function isn't going to prevent the return. I don't want it to run this whole job and then not give us the results back.
No, this should be fine.
I'm going to remove this because we're now running that. The first two, try x3 and try x4, I'll remove here because we're running them. Okay, let us submit it. Oh, one thing I need to do here. That's line 186. Well, I can just take this thing here and I can say job status. Okay. Let's take that thing there. Okay, looking good. Okay. All right. Our next topic, the thing we really wanted to do. So actually this, I need to remember how to package this up because it's actually going to go in a different section than the one that I thought we were going to put this in. Okay, the purpose of the thing we were actually going to do was looking at the empirical metamathematics question in MetaMath, okay, or other places. I mean, we're asking, so one empirical mathematics question is, where in the entailment cone are interesting theorems of mathematics? And I think we're answering that, and the answer is they're pretty far away in the entailment cone. That is a pure, if the universe was just doing our mathematics for us, in other words, mathematicians have done a big selection effect to find the theorems they care about relative to what's in the entailment cone. Which is interesting. Now, the question is, if there is an entailment fabric, how does it relate to that? Can we, let's see, can we work out an entailment fabric for the axioms of Boolean algebra? So we want a shallow entailment cone. How will we do this? We want shallow entailment cones around every theorem. And then we want to see whether those overlap.
For what? For one iteration?
Well, let's say, yeah, but I mean, that would correspond to, what is the analogous thing for an entailment fabric here?
That sounds fine. You take the entailment cone for the original axioms, you go one iteration, and then you take those theorems and you take their entailment cones. It's a minimal fabric, right?
Mm-hmm.
Yeah.
I think so. All right, let's do it.
One fabric, one axiom iteration, one theorem iteration.
Right.
Right.
Okay, so let's do this.
Yeah.
Okay. Okay. A 1-1 fabric. Okay, so that is one iteration for axioms,
Yes.
one iteration for propositions, we might call them.
Yeah.
And those
Okay.
propositions might be true or they might be false from the axioms. Right? The propositions might be false from the axioms. So then they will not join up with the entailment cone.
Oh, I see how, okay, I see what you're doing here. Okay, I see. So you're saying the propositions are the inhabitants of the entailment cone of the theorems that are in the entailment cone of the axiom. That's what the propositions are. Yeah. Is that the case?
So hold on a second. So what I'm imagining is make entailment cones
Yes.
for the axioms.
For the axioms.
Make them for the propositions. Do these entailment cones overlap?
But why not just use the term theorems? I mean, that's how we normally describe the inhabitants of the entailment cone of the axiom. No?
I know, but these aren't the inhabitants. Do these entailment cones overlap? I.e., are the propositions theorems in this axiom system? Because this might be just some totally random proposition, which simply doesn't join up with the entailment cone from the axioms. See what I'm saying?
Hold on. You're saying if you take the second order entailment cone, yes, the leaves of that cone, so to speak, are those the propositions? Is that what you're describing as the proposition?
No, I'm asking if you iterate from the propositions and you iterate from the axioms, do they do the results overlap?
Okay.
We got light cones coming from the two things. We want to know,
I
do
understand.
they reach the same place? I mean, I have to say, it is, the thing which is very bizarre about this, okay, and I still need to understand, the atoms of space are unnamed, except maybe in the center of each black hole. Right? Most atoms of space are unnamed.
As are EAMs, besides the general, appellative. Yeah.
But axioms, these theorems are not unnamed. They have names. These theorems made from giant collections of EAMs have names.
Now, what do you mean by names? I mean, some of them are human named.
I know that, but I mean, they have at least symbolic representations.
Yeah, right.
That go
right.
beyond, which are somewhat human interpretable.
Yes, right. Even the ones that are unnamed, they are still symbolically interpretable.
Right. I mean, so what we're saying is the atoms of axiomatic mathematics, i.e. statements, are are somewhat human represented, are somewhat human readable. Okay, as opposed to atoms of space, where there just isn't any name. In other words, there's some semantic communication from the structure of the atoms, from the structure of these statements. You can read them, whereas, telling you what the atom number, I mean, amusingly, the only atoms that are named are the black holes, so to speak. The only atoms of space that are named are the black holes. There's just one, well, I don't know, it's one atom of space in the center.
Yes, but I mean, we can have versions of these where you have dollar signs, and you have arbitrary operators. I think there's a finer point to this. I mean, at the EAM level, it doesn't have to be recognizable at all. And understanding how you get from that to what's recognizable. I just wonder if some of it is a design decision. Some of it is a design decision on our part to make it more interpretable, I think, when we're doing this, when we're making these graphs.
Sure.
Yeah.
All right, let's do this. Okay, so what we're going to do, if we run this is our sort of sample entailment fabric, just from this, okay? And Okay, this was a two-step running of an entailment fabric. Okay, sample string-based entailment fabric.
Mhm.
Okay, so now the question is, now we want to do a true expression entailment fabric. Okay, for which we want the entailment cones of some of our very favorite. So we basically want the entailment cones of,
Boolean.
yeah, we want the entailment cones of the notable theorems, and we want the entailment cones. Okay, so here are the notable theorems. We want, okay, entailment cones for these and entailment cones for the axioms. Okay.
And I think what Nick and I found is that there are really two Boolean axioms that have kind of non-trivial cones. And those are the two that generate variables. The other ones are somewhat trivial, we found.
Oh, well, let's check that.
Yeah.
Okay, so we want a token event substitution graph, if I'm not mistaken. And then we want this for one step.
Why,
Actually, we want that.
Why substitution?
Well, it should be by substitution.
Okay. Okay.
Well, actually, let me do this. Oops, what did I do wrong here? What did I do wrong here? Oh, what do I do? Token event. I've got an axiom there. Do I have to put it in braces?
Yeah.
Okay, this is the one-step consequence of every one of those axioms on their own. Now, I don't know whether it's the case, whether these, in fact, have a non-trivial entailment fabric. So what we want to do here is just like we did up here. That's amusing what I did there. Edgeless remove events. What does the string apply? Oh, I see. That's the token event graph. Okay. All right. So let's try and mimic that here. Okay, so these are the rules now. Where is it going? Well, maybe we shouldn't do this. Maybe we should just do this. Okay, so down here, this is remove events of not that, but do you understand what this is doing?
Kind of. We just run. You already generated those token event graphs, right?
I know, but I want to rerun them. I want to rerun them inside here. So I'm generating token event graphs. What is this rules thing doing here? So this is trying to get. Oh, I see. All it's doing here yes, it's for each graph, right? It's coloring the edges of each graph so we can see which graph is which.
Mhm.
Yep.
Okay, what is the rules doing here? Oh, it's mapping over the rules. So in fact, what we want to do here this should be our rules thing. Let's forget the options for a second. Okay, so here, do you understand what should that have been? Hold on a second here. How do the rules? Oh, I see. That's adding the rule to the edge. Am I making sense? Oh, that's the style of that edge. Okay, so that appended the rule designation to each edge. But here we've got the edge list. Where are these rules? Why are the rules? Oh, there's.
So A
I
is the
see.
rule and B
Yeah.
is the index.
I see. So here we go. So this should be the rule there, A, and B is the index. Let's try this. Okay, that looks plausible.
Right.
So that's, what's that?
Yeah, and they're the two.
Okay, so let's see who those friends are there.
Right.
That's kind of messy. Well, let's say vertex labels. Okay, so there's one overlap there. Oh, great. The overlap is A goes to A. Okay, so now, if we were to go 2 steps here, I would say we should forget about this. Oh, we might need to have a, so these are variable generating things up there,
Yes.
those top ones.
That's right. Is it still a two-way rule A?
It only has one friend in common. That's kind of pathetic for an entailment fabric. It's
Well, but what does it say about the?
it says
these
the axioms are
Boolean
fairly
axioms?
independent.
Right, exactly. If they had tremendous overlap, I don't know, would they be inefficient, or could some criticism like that be made
Yes,
of
that's
them?
true. Yeah,
right?
but if they had a lot of overlap, then you might not even need to use all of them separately.
Right, they're probably not minimal. Like minimal axioms, their entailment fabric should be rather fragmented, I think, if they're efficient.
Yes, I agree. I
Yeah.
agree. So okay. That's a nice picture, though.
It's two coronaviruses shaking hands, right?
Yeah, well, we could think of it as a. We'll not give the immunological interpretation yet. Okay, so let's get the notable theorems and let's map over the notable theorems and make the entailment cone for those. Okay, the common entailment cone for this and the notable theorems. So, we want the corresponding thing for notable theorems. So here, instead of Boolean axioms there, well, actually, I could just do this. That's very easy. Look. Okay, hold on. So if I say axiomatic theory, Boolean axioms, notable theorems, I will get that. And I just have to say, I believe, I just have to say values of that. And I say flatten, just for good measure, because we know there's only one of each of them. And then I say axiomatic theory TWP. Lovely. And now I need to do that circle wedgie thing. Okay, let's just do one step here. Okay, now I'm going to make one other change, which is I'm going to make I'm going to change this to be green for reasons that we'll see in a moment. It's annoying that doesn't look, these don't look different. Why not they look different? I'm blending green into why don't these look different? Into this arbitrary hue. Why wouldn't they look different?
I don't know.
You can't be serious, but that. Now, why aren't those blends? What's going on? If I take that orange and I say blend, oh, silly me. Let's just do a full blend like that. Forget the echo.
Better.
I don't know why they're
Even
so
better.
light. Yeah, I don't know why they're so light. Why are they so light? Well, who knows? Doesn't matter. That's not the important thing. Okay, so let's take this. And then what we're going to do is take this guy.
Right. So this is
And
the
we're
first
simply
one.
going to give the two
Right.
two graphs together. We're just going to combine the graphs, I think. We're just going to combine the, what do we have to do to combine these graphs? We literally put the two graphs together.
Can you union them?
Yeah, but then we'll lose all the color information.
You can't union them without
I have a
forfeiting the information.
version. Well, I have a graph union version that kind of preserves colors somewhere
Okay.
because I already tried it.
Well, I mean, we can clearly do it by just saying graph of union vertex list / at oh, this won't work actually, but let's see what this does anyway. I need to preserve the colors, otherwise it's not going to work. Anybody know how to do this? Brad, any thoughts?
I just sent you a graph union that preserves edge style.
Which, by the way, we should probably make the default graph union do that, and that's probably something for Charles. Can somebody feed that to him?
Sure.
That's probably what default graph union should do. Well, that wasn't good. Well, do we have to symbolify the vertices? Oh, come on. Improperly formatted option. For what?
Wait, what a union? Oh yeah, fine.
I hit the error button, it's spinning. Let's hope it manages to resolve. Okay, so what this should be doing, let's read your code. Is it in fact, okay, an annotation value? Okay, but the thing we can already see here. Oh dear, what is happening here? What's going to happen is I think we will gradually see these pieces of, yeah. Okay, all right, what do we do here? What went wrong? Or can we just write this by hand?
So
So
does
we've got-
annotation value edge style work at all?
Sorry?
Does annotation value work on those graphs separately or not? This looks weird.
You know what? These graphs have, I included edge tagging in these graphs, which we do not need. See those directed edge, that they're tag directed edges.
Right.
And I believe that's unnecessary. And I believe that was added in, let me look here.
You append there.
Yeah. Okay, so let's take these. Let's redo them. Without the append. Style. We just say hash here. Okay, now let's try your graph union. Now, do you think we have to do the vertex replace still? We might have to.
Yeah.
Oh, come on. What is it doing? Huh? Okay, so let's take this and let's do the annotation value of that, comma edge style.
Or maybe because colors are in list. No.
Well, look, very least is we can just get these annotation values out and reapply them. Okay. So new graph union, G1 blank, G2 blank is graph union of G1, G2. And then we basically want to say edge style goes to flatten of I think we better do that symbolified patterns on everything. Flatten of annotation value hash edge style slash at G1, G2. Okay. Now let's say okay, now where are those things here? We did get a graph union out of this, right? Unless those edges have been subsumed in the other edges. Am I making sense? Let's compare that with this graph here. Well, they may have been. So I think we want to make these more dramatic. So let's try making this well, let's just for the hell of it, let's do a version of this where we just make that red. Actually, I'll tell you what, well, let's do this. Let's make the edge style here be thick. Gonna work with a hue and a thick there. What do we need to use a directive? What the hell did I make a mistake here? Okay, what was this right? Hue of fractional part. Oh, the blend is all the way out there. Never mind. RC, so what I want to do here is RC. Actually, I just want to say thick there. Great. Oh, cool, cool, cool. That is a fabric being put together. There are the axioms and there are the propositions and the things knitting itself together. That's really cool.
Very cool.
Okay, so let's go one more step. So we want to do here, these here, we might want to limit the size, but we can try this. This may not be a good idea. And this one we also know got very big. So let's, maybe we want to limit the size. Where do we put the size limiter in?
The document with pattern test.
Let's let it run while I go find it. We had that in our other notebook. Where was it? That was here. Okay, token event substitution graph there. And then pattern test, let's say less than 10 for right now. Okay, it's quite lovely. So those are our notable theorems. Those are the relations. That is the knitting together. Every different color represents a different theorem. And that is how those theorems knit themselves together in this entailment fabric. That's quite lovely, actually.
Well, right now they just only need themselves through this A equals A thing.
Well, that one does better.
Yeah.
Yeah, you're right. That's a bit unimpressive there. Okay, there are the axioms. So now we have to say new graph union. $227 and $226.
Okay.
Well, I admit that truth is the only common theme. Right, there are the axioms. Well, actually, not completely. I mean, those axioms, I can't really, yeah, they've knitted themselves in other places here.
Yeah, independently, they can't really do anything interesting.
Right, because the axioms themselves are somewhat separated.
Yeah.
Or maybe with by substitution, they can do something. There's going to be more knitting together.
All right, let's just try this. We'll live dangerously. Let's just try this by substitution. How do we do that with the token event substitution graph? Do we have a...
Just rename it. Yeah.
Yeah, we were doing that already.
Okay. Well, let's do this up here. We should clean this code up. Still, they're only friends in one place. Oops, did I just? Oh, I got rid of the wrong thing. There it is. Oh, that one has a few more friends. Okay, there's some additional friends here.
Yes, yes.
30 to 29.
Interesting.
Not thrilling.
That's more interesting. Can we do 2 iterations?
Let's try it.
Okay.
See what it does, if it does it. Let's reduce it. It probably won't be interesting, but we could try reducing it. Let's see if it does anything. Or it's just hopeless. It's not encouraging.
Maybe it's fine. Just wait a little bit.
Okay.
Let's try this one. Truth is a common theme, but not a lot else.
No, it's
Okay.
not much more interesting, but it's nice to have.
Yeah, these are nice
It's
pictures.
nice to have examples for at least 2 iterations.
Yeah. All right. The thing that I was hoping thing I was hoping we were going to be able to do, but perhaps you know, the question is from like the MetaMath system database. What did we think we were going to learn? What we wanted to learn there, I mean, in a sense, it contains a bunch of proofs. Okay, so for example, we could imagine making an entailment fabric from what it contains. It contains proofs.
Yes.
Yeah, let's just make a note of what we're looking at. Oh, actually, I just want to see. Oh, okay. Okay, so the MetaMath database contains proofs. Now, those proofs, what structure do they have? Do they have the same structure as our proofs where it's two theorems go in and one comes out? Is that right?
No. There's a different substitution strategy.
What is it?
Well, each theorem, it's still just substitution, very basic one when you just replace variables. But you can you don't have equality basically, right? It's just a substitution of terms. So it's not two-way rule or equality at all.
Wait a minute, two-way rule or equality, what the heck is it then?
So just every axiom or theorem contains some variables, and you can substitute whatever you want for them.
Okay.
And you have to introduce equality on your own, basically. So if you have a MetaMath database with equality, then this equality introduced by hand.
Why didn't we do things this way?
Or we can do it like when we just manipulating expressions without equality with some rewriting rules. That's the same thing.
With which?
Any rewriting rule, like take any system, right? If you're just doing rewriting, that's essentially the same thing. There's no equality inside.
But our whole setup with two-way rules and a cumulative evolution, why do we need that?
To make shortcuts in proofs.
And to make what we've got look more like traditional mathematics.
Right.
Although MetaMath does surprisingly well without that, you're saying.
No, there are still shortcuts, even within one proof. You still can name a theorem and use it multiple times in one proof, right? So that's kind of the same shortcut thing. It's like naming a theorem is like creating new equality. It's like stating if you provide this theorem with its inputs, it will make an output. So you can just insert this inline path, inline statement for this particular theorem. So yeah, it's just more general in a way that doesn't include equality.
Sorry, say that again. I got distracted by something, but please go ahead. What were you saying? Just repeat, excuse me.
So what MetaMath has Mathematics have theorems that you can name, right? And proofs when you can basically link to those theorems, maybe multiple times within one proof.
Yes.
So how is that different from substitution lemmas within our proof graph, for example?
Is it different? I don't know. Doesn't sound like it's different.
It's different in a way that it's not necessarily equality. Each theorem statement can be anything, not just equality. It can be any proposition, but you can still use it, right? Equality is just one kind of proposition, and it's special because we can take any path in our proof. So if we have like rewriting sequence, when we just rewrite one term into another, we can just, as soon as we prove this sequence, we can just say that those terms are equal and state it as a lemma, right?
Yes.
And we don't have to like expand this path.
Yeah, I understand.
Later.
So it's rules rules acting on rules.
Right. But you can't do it like with arbitrary proposition.
You cannot do that, right, with arbitrary propositions. The arbitrary propositions don't make rules which you can apply to something else.
Yeah, that's the point.
Okay, but so what do we learn? Okay, so if we have a graph, what is the analog of our proof graphs from MetaMath? So it's using certain theorems. It has things which are not theorems. They're simply, well, they are theorems, but they're not our kind of equivalence theorems. They're not theorems that allow you to do a rewrite. They're just
Right.
an end in itself, like this is prime, for example.
Yeah.
Okay, so it's not really true. It uses, okay, so some of its theorems do not correspond to rules that can be applied subsequently. Right?
Yeah.
Sorry, doing something else here. Okay. Well, so my question is, can we take that database and basically make proof graphs? The question is, for some area of mathematics, there will be a bunch of proof graphs. I think this is what we had made before, is it not?
Like
That shows which theorem. So one of its proof sequences is like our proof graph. I mean, it will have a bunch of essentially substitution lemmas but there will be statements there that cannot be reused in other substitution lemmas. Right? There'll be some statements that are theorems that can be used in other substitution lemmas and others that cannot, if I'm understanding correctly.
Well, it's a little bit different from substitutions alone. It's like metamath proof. It's more like substitution of variables. They always look like novelty generation. You just replace a variable with something, and just a human tells it with what to replace it, your variable. But when you combine two equalities, you can combine it in just so many ways. You have to specify position when the rule is applied, its orientation, and you can unambiguously apply one substitution or one equality to another using substitution, or by substitution.
Yeah, right. But I mean, but that's the same as, I mean, in our theorem proving, look, all of our events effectively have inside them tagging of the you know, let's see. I mean, they implicitly have that information. Am I making sense?
Well,
They implicitly have
explicit.
every substitution is a substitution for a particular part of a particular expression in a particular direction. It's just we don't usually show that.
Right.
But MetaMath is showing that, just like find equational proof shows that in its proof data set.
Well, not with position, but it just knows where the variables are, and it just replaces the variables.
Oh, I see. You're saying MetaMath doesn't need to know the position because it has named variables. Is that what
And
you
it
mean?
only allows, and it only allows to substitute for variables and not just for an arbitrary term and make some kind of match against it.
So it has no pattern matching. I see. It does not.
No, pattern matching will happen like when the human will explicitly provide a theorem with some statement, right? Or a lemma that produces a statement. And when this will match, well, the matching will still happen, but variable is going to be replaced. So it's kind of a substitution in a way. But it would not without a position. I think it's only like only happens at the root position.
Okay.
Or the
Okay, but so my question here is, what can we learn from this? So in other words, we're trying to ask the question, somehow, what are the notable theorems? And I mean, first question is, what are the notable theorems in some field? Notable theorems and their proof distances, right? This is the network which shows essentially, this is like the entailment fabric for some random field of mathematics. It's showing how far it is from, it should show us essentially the distance matrix by proof steps between different propositions, between different statements, should it not?
yeah. Okay, let's try it again. What are you trying to say here?
So what I'm asking is, okay. Let's see. Okay, I'm trying to understand from the MetaMath database. We've got these entailment fabrics that we have done with our own theorem prover, right? That we've done by automated theorem proving.
Mhm.
See what I'm saying?
Mhm.
What this is a hand-constructed, a hand-woven fabric. See what I'm saying? Artisanal.
Ours.
The hand-woven fabric, basically. Does that make sense? I mean, isn't that what that's doing? I mean, it's saying what the connections between theorems in this field of mathematics are based on hand-constructed proofs. Am I missing something?
No, I don't know. What do you mean by hand construct?
Yeah, what do you mean by hand?
Well, I mean, the MetaMath database is a proof assistant-like database.
Yeah,
The database
yeah.
of proofs that humans have constructed.
Okay.
Yeah,
Okay,
yeah.
and so what we're saying is there should be a graph that
Mhm.
shows for every, okay, so every theorem has a proof that has multiple steps, and each step is using some other theorem.
Right.
So it's a great big graph of the interdependence of theorems. Am I right?
Right.
Yes. Yes, you're right. A graph of the theorems that human mathematicians care about.
Yeah.
Yeah.
Yeah. Human mathematicians, it's only, but I mean, the proofs may contain lemmas that people don't really care about. But so what I want to get at is this structure. This is what we've been asking, looking at for ages. And I think you've got something which is essentially something like this. If I'm not mistaken, I mean, this is what we had, if I'm understanding correctly, this is what we had back last year, whenever it was, 2 years ago. Oh my gosh. In here.
In the Euclid post, yeah.
Right. So this here,
Mhm.
I think this is the thing. This is the right thing. This is the theorem dependency graph. But it isn't necessarily showing every step in each proof. It's showing which theorem depends for its proof on which other theorem. It's not showing each step. So the only difference here is that it's not showing each step. It's just showing the overall dependency.
Yeah.
Okay?
Yeah.
So if we could extract just showing each step, then what we will see there, okay, so what are we going to see? We're going to see the entailment fabric for human mathematics. And the only question would be, it seems to me that the only question that's likely to not be a big ball of wool, basically, is something I mean, is something a bit like this, which is showing. This is showing the dependencies between different domains, which is a much more macro level thing than we've looked at before. We've been looking down. I mean, we're, going from the level of the eames to this level is a long way.
Yes. Yes.
And this thing here is showing us, I mean, this is more like the overall architecture of, I mean, this is the structure. I mean, what we're claiming is that the homogeneity, that this is an arbitrary labeling that people have put on metamathematical space, and that in fact it's more homogeneous than this.
It should be, as human mathematics progresses, we should find further connections between these.
Right.
That's the point.
So, so this is basically what happens when people first populate. They first move into the landscape and they build encampments in different places. It turns out in the end, they farm the whole area. If you see what I'm saying. In other words, these are the early encampments in metamathematical space made by mathematicians.
Right. But there are passages, etc., that can be taken, but they have to be found first. And you might have to go through the bush, so to speak, in order to find.
Well, yeah, you might have to go grind yourself down to the eames and come out the other side.
Yeah, that's the bush. That's right. Yeah.
Right. But that's the question of how much. Okay, so that is the relationship between these. This is basically the early encampments, and so it'll be kind of interesting to see for some area like logic. It will be interesting to see what something like the MetaMath database actually says. But I have to go to some other meeting here. But we've achieved quite a bit. I wanted to see what happened to that job we were looking at, just for where was it? It was in ATP, I think. Just see what happened here. Job status, running. Job status, running. Okay. Well, we'll come back later, see what happened. All right. Thanks a lot, guys. So we'll continue separately. And let me just check one thing here, then I really need to go. Okay. See you all.